Welcome. Today we will be taking a look at the notes worksheet entitled Inverse Functions Day 1. And so this will be the first day of a 2-day set, which means today just represents the introduction and kind of the build-up of the concept behind an inverse. And then day 2 would be more of the formalized algebraic version. So we'll kind of see that tomorrow. So let's start it out. Looks like I have this pretty long definition here on a particular type of function, and then we'll sort of get a little bearing on what that is, and then utilize that over the course of the lesson. So here we go. At the top of your page it says one-to-one function, and so this would be the verbal description of it. Let me read it as slowly as possible here. For each x in the domain, there is exactly one y in the range. And as a matter of fact, this of course is our definition of a function that we saw first semester. Each x can only produce one y. That's what that says up above. Now, there's a second piece that makes it one-to-one, so a particular type of function. And so here's the and. No y in the range is the output of more than one x in the domain. And as it says on your paper, this is the one-to-one part. So what that second part means is exactly what we'll go through on example 1 and see if I can lay it out for you in as visual a way as possible. So let's do that. At this stage, it's probably just a whole bunch of verbal jargon. Let's see if we can make sense of it though. So example 1, it says, use the 3 mapping diagrams to determine if the relation is a one-to-one function, a function but not one-to-one, or not a function at all. So here's what I'm going to have you do, everyone. If you can give me sort of 3 pairs of ovals side by side. It's been a little while since we've seen mapping diagrams. In fact, I think when I taught mapping diagrams, I said it would come up maybe 1 or 2 more times over the course of the year, and this is definitely the lesson I was thinking of at the time. So something like that, just 3 pairs of ovals. And what I'm going to do is just put some arbitrary numbers into the left oval, and those are going to do what is called map. They're going to map to numbers in the right oval. So these are going to represent our x's, and these are going to represent our y's. X's mapping to the y's. And so everybody, let's just do a 1, a 2, and a 3. So I'll have that map there, there, and there when you get an opportunity. Okay, now everyone go to the second one if you would. I'm going to go with the same 3, and again, these are just totally arbitrary numbers, just easy for me to use. And then let's go 1 and 3 over here, please. And I'm going to map this way. Okay, so that will be our second relation, x's mapping to y's. And then the third one, let's go with the same set. And how about you run a 1, 2, 3, 4 right down there. And here's how I'm going to map. Okay. Now, here's what I would ask you to do. Pause the video for just a moment, should be all it takes, and tell me which is which. Which one of these is a particular type of function, what is called one-to-one, which one is a function, but just not one-to-one, and which one would not even represent a function at all. So think about that for a second, and then come on back and let's figure it out. All right, well, let's see how you did. I'm thinking the one to the left matches our verbal definition perfectly. Each x produces one y. This produced that, and this produced that. Each x produces one y, so it's a function. And no y in the range is the output of more than one x in the domain, meaning each y only comes from one x. The 1 comes from the 0, 2 comes from the 1, and the 3 comes from 2. One-to-one. This one produces that one, and this one only came from that one. So guys, this is a one-to-one function. All right. How about the other two? This one right here, I would say is a function, definitely, just not one-to-one. And let's see why that is. So remember a function. This x produces one y, this x produces one y, this x produces one y. But as you can see, this one right up here, that output is coming from more than one input. It's coming from the 0 and the 1. So it's not one-to-one. And in this one over here, I think by default is of course not a function. And remember, by definition, we've kind of talked about this a variety of times before, but I think that's our dilemma right down there. In a function, the 2 cannot go into the function and produce both the 3 and the 4. It simply does not work. So I think that's it. Those are your 3 right there. And I'm hoping now that definition makes a little better sense. We will definitely see the tie-in to this with inverses as we go through, but let's do 1 or 2 other things first. So let's see. Let's read this question and then the one that follows it and see if you can get the second question based on my inflection on the first. You ready? How do we determine if a graph represents a function? Well, if I just took a look at any particular graph and performed the vertical line test, that would immediately tell us if it is a function or not. Perfect. So, what would be your intuition here, everybody? So it has to pass the vertical line test to be a function. Once we know it's a function, well, let me say it correctly. How do you think we will determine if the graph of that function is then also one-to-one? So I don't know if my inflection helped there or not, but it is what is called, of course, the horizontal line test. And it works in the exact same way. So if you don't remember kind of what those tests represent, well, just wait a second or two. But basically, I would ask you to do example 2 on your paper, and it says determine which graph represents a one-to-one function. So 2 functions, by the way, both pass the vertical line test. This one just happens to be a nice, probably like y equals x squared. This one probably is something like y equals x cubed. No big deal. So one of those is one-to-one, and the other is not. And the winner, that one, there it is. So this is a one-to-one function. And because it passes the horizontal line test perfectly, no matter where I draw a horizontal line, it's going to touch in only one spot. And I know a few of these points right here. Here's 1, 1, as a matter of fact. The 1 produces the 1, and the output of 1 comes from 1. Each x produces one y. Each y comes from one x. Unlike, let's see if we can spot this one. Here we go. Here's a good spot for it. Something like that. Notice it touches in more than one spot, and as a result, does not pass the horizontal line test. And watch that definition in action, everybody. Here are a couple points on the graph. There we go. And do you see? Of course, each x does produce one y. It is a function. But notice the y. Do you see that y value of 4? And do you see that it's coming from 2 different x's? If it comes from 2 different x's, it is not one-to-one. So it's a function, just not one-to-one. All right, I hope that works for you. So just a nice looking horizontal line test quickly to determine if the function is one-to-one. Now let's sort of move along here a little bit and talk about inverses. As I said, we'll develop in a very conceptual manner today and then formalize it up a little bit on tomorrow's notes worksheet. So let's start it out here. And this is actually a sentence that I put on a previous notes worksheet. In fact, I was probably pretty melodramatic when I came across this and said it was, for the most part, probably the most important sentence of the entire semester. And if we understand this, it really opens a lot of doors up with what you do with functions. So it says, a function is a set of rules telling us what to do to the input. The input goes in, the function manipulates it, out comes an output. So the analogy that I'm going to use here today is it's like wrapping a gift. And you'll have to follow my lead on that as we go through, but give it a little time if you would. So it's like wrapping a gift. So an inverse function, and by the way, everyone, here is the notation for an inverse. This is f inverse, by the way. An inverse function of f undoes whatever f does. So if my analogy for creating a function is like wrapping a gift, then the analogy for creating an inverse is it's like unwrapping that gift. So that's all I want you to write in there. Now before we do example 3, just one thing to note on the notation piece right here, because this definitely comes up. It looks like a negative exponent, everybody, but it's not. It's not. This is not 1 over f to the first. That's not how this is played out, everybody. This is just very simply the notation for talking about the inverse of f. So just kind of note that piece right there. That does not mean it's the reciprocal of f. Totally, totally different. Okay? I hope that helps. All right, so the easiest thing to do, the best thing to do in my opinion, is to just kind of start it out with our most basic family of functions, which would be linear, of course, and sort of give a verbal description of it, relate it to my wonderful analogy, and then see if we can create our inverse, and then also see if what it looks like graphically. So let's get it started. If I gave you an input, could you verbally describe what you would do to the input in order to produce the output? So letter A says, describe the function rules. And I'm hoping that you would agree with me that basically whatever the input is, we would multiply the input by 2 and then add 3. Okay, that's great. In fact, I'm going to put a little 1 right here and put a little 2 right here. 2 function rules to go from input to output. Now, here's the thing. We're going to then sort of try to create our inverse starting with our generic input. So everyone, it says start with the input x and undo the function. So here's where the analogy comes into play. And this is either going to be very helpful for us or it's going to be a catastrophe. We shall see. So here's the premise. Wrapping a gift, think about the rules, think about the steps you take to wrap a gift. You take the gift, you put it in the box, then you put the wrapping paper on top of the box, then you put the tape on top of the wrapping paper, and then you add the bow. If I ask you to unwrap that gift, what do you start with, everybody? You start with the bow, and you work backwards. Is everyone okay with that? You would undo the bow, you'd undo the tape, you'd undo the paper, and then you take the gift out of the box. You go backwards. So if these are my steps to create the function, I'm going to undo them working backwards. Everyone okay with that? So in this case, I would go ahead and my first order of business would be to undo adding 3. So I would subtract 3. So everyone start with x and very simply subtract 3. Okay, so that's where I am at this stage. Undid this step right here, and now I'll undo that first step. How do I undo multiplying by 2? Divide by 2. And that, in a nutshell, take the whole thing and divide by 2, that is the inverse. And so when we undid the steps of the function, we created its exact inverse. And so let's throw some notation on that. Make sure I have that for you. So the inverse of f of x, that's how we would read this piece right here. And let's make sure I have that. There we go. So the inverse of f of x is equal to x minus 3 all over 2. All right, that's good. We'll get some more practice on this, of course, but for right now, how about you box that up for me? Now, a couple things that we're going to see here. So it's time to get the graphing calculators out. C and D go together, by the way, so let's tie them together. And then what we're going to do is create some conclusions based on this. So by the way, take a look at the function. It says, is f a one-to-one function? Here is f right up here, defined by f of x equals 2x plus 3. If I asked you to graph that on the coordinate plane, which we'll see momentarily, but you would all know it produces a line, y-intercept is 3, slope is 2. Will that pass the it'll pass the vertical line test. Will it pass the horizontal line test? Yeah, sure. And so as a result, it is definitely a one-to-one function. So now, everybody, what we're going to do is graph the function and the inverse on the same coordinate plane, and then independently, I would ask you this. is the inverse of function. So it is time. Let's bring that calculator up and do a few things with this and start to generate some conclusions and some good stuff with this. So first and foremost, go to the y equals for me if you would, and type in 2x plus 3. And I'm going to go ahead and just quickly zoom standard, and without question, that does pass the horizontal line test. It's 1-to-1. Now, what I'm going to do is go down to the y2 and type in the inverse. So this would be, everyone, x minus 3, and then divide by 2. Now focus on this piece. What I'm curious about is just this independently. Is that a function? Does it pass the vertical line test just by itself? Let's take a peek. Well, here's the graph of that inverse. Does that pass the vertical line test, everybody? Is it just a function? Sure. Yeah, it definitely is. It's just a line, very similar to the other one. And so as a result, the answer is yes. These two answers, by the way, will always go hand in hand. If the function is 1-to-1, then the inverse of that function is a function independently. And that gets us to our next piece. So you'll see, and we're going to have to develop 4 of these as a matter of fact, but that at least is going to be conclusion number 1. So that finally is a little tie-in from the beginning of the lesson to the title of the lesson. So here we go. If f is 1-to-1, then the inverse is a function sort of by itself, independently. If you don't want to write independently, that's fine. It's sort of a redundancy, but I'll go ahead and write that in there. And as a matter of fact, the unit that we're going to start to really work on in just a little bit talks about 2 families of functions. And as a matter of fact, the relationship of those 2 families of functions are that they are inverses of one another. So this is why the inverses are kind of taught right before our upcoming unit here. Okay, so number 1 taken care of. There happens to be a nice reflection piece with the graph of a function and its inverse. So I'm going to do a couple things up here. I have them. It's a good window. I'm going to try to square this up, everyone. You don't have to if you don't want to. But I'm going to go zoom and hit number 5. I'm going to try to make all the tick marks the same. And it's not ideal. Now here's what I'm going to have you do. Go back to the y equals. And I'm going to throw in a little boundary line right in there. A reflection line, I should say. And I'm going to hit graph. And so I graphed y equals x. And if you sort of look at it, again, it's kind of tough to tell with these graphs, but we'll see them coming up and it'll be much more apparent. But basically, if I took the graph of the original function and folded it over that reflection line right there, it would land directly on the graph of the inverse. These two should be perfectly reflected over that line right there. Again, we'll see it in action a little better on the last example today, and certainly on the ones tomorrow. But for right now, let's jot that in as conclusion 2. So actually, let's do it this way. Excuse me. I'd like to phrase this in a slightly different manner. So the graphs of a function and its inverse are reflected over the line and defined by y equals x. There we go. That looks good. And so we've seen reflection lines before when we did transformations and some symmetry parts. We saw x-axis reflections and y-axis reflections and stuff like that. Here we have a reflection over the line y equals x. Okay, good. Now 3 and 4 are going to go together. So let's see if we can do 3 and then draw a conclusion to get 4. I'm going to bring the calculator up again, and I'm going to track some points. I'm not sure if you remember when we did transformations, but in transformations we talked a lot about the original point and then the corresponding point. Well, as a matter of fact, the same thing occurs here. The graph of this function is made up of an infinite number of ordered pairs. Those ordered pairs changed in a very particular way to make up the ordered pairs and hence the graph of the inverse. And so what I'd like to do is track it a little bit here and see if we can get those corresponding pairs. So how about this? Everyone hit second trace for me. And let's go to value. And I don't know, I'm just going to find something here. I'm going to do 3. What the heck? And everyone type in x equals 3 and let's see. All right, there it is. So this just happens to be one arbitrary point on the graph of the original function, 3, 9. Well, guys, what I want to do is track that point. Where did it go on the inverse? And here is how it's going to work. Everyone go on back, second trace, go value, and in this case, instead of hitting 3, hit 9. Now you're going to hit enter, and you're going to be like, what? But the problem is we're still on the function. Let's get on the inverse. So everybody hit the down arrow for me if you would, and now we're on the inverse. So here everyone was 3, 9. Now look at the one on the inverse, 9, 3. And they switch. And that's what happens. I'm going to confirm. Let's just do one more. I'll just be quick with this. How about 2? So there's 2, 7 on the graph of the function. And everybody, let's go back and do it one more time. How about 7? And there's 7, 2. And by definition, that is our relationship between all the points that make up the function and all the points that make up the inverse. The x's and y's switch. So let's do this. If x, y is a point on the graph of the function, so another if-then statement here, then very simply, those numbers switch, and so y, x is a point on the graph of its inverse. There you go. Okay. Which draws a pretty interesting conclusion for number 4. So 3 we kind of worked through, but now it's time to put 4 together. And it all deals, everybody, with domains and ranges. So let's track this one. So the domain of the function would be all the values that make up the inputs of the function. That would be all of these values right here. Now the way we've created our inverses is all those values have now moved. Instead of becoming the input, they then become the output of the inverse. So all the values that make up this quantity right here, the domain, now make up this quantity right here on the inverse, or its range. And so as a result, everyone, the domain of a function is the exact same as the range of the inverse. And here's the interesting piece, which we have been unable to deal with at this stage without use of the graphing calculator. Every time I've asked you for the range of a particular function, you've had to interpret it from the calculator. You've had to graph it and think about it vertically and come up with the range. But now, if you look at the range of any function, you can see that all of the numbers that made up that set right there moved to the input of the inverse, or the domain of the inverse. Domain we can work with algebraically without too much difficulty. And so if we know what this quantity is, it's the same as this right here. Wow, that's great. Okay, so I figured we would do just a couple more examples to round this out. And let's see, example 4. So let a function be just a set of ordered pairs. And remember, everyone, there are a variety of ways to represent a function, either a table, a set of ordered pairs, a graph, an equation. Here it's just a set of ordered pairs. And very simply, if that set of ordered pairs makes up the function, then, and I don't know how to draw a bracket to save my life, so I'm going to do just some squiggly lines right there. Well, the inverse is made up, by definition, of switching all of the x's and y's. So instead of -1, 5, well, 5, -1 makes up part of the inverse. 2, 1 instead of 1, 2, 5, 3, and And 8 comma 5, right? Wait a minute, I have that. Yeah, I'm sorry, 8 comma 5. Okay, very good. Now actually I would ask you one thing about this particular problem, and then we can kind of move forward. Let's make one connection before doing example 5. If you look at this, everybody, I guess I would ask you this. Is this a one-to-one function? Take a look at it in detail. Is it one-to-one? It's a function, right? Each x does produce only one y. Is it one-to-one, everybody? No, it's not one-to-one because of this piece right here. That the 5 is coming from -1 and also 3. So look at the conclusion above on your paper. If the function is not one-to-one, is the inverse that we created, is it a function at all? And no, it's not. And here you can see that this makes it not a function. So if the function is not one-to-one, and you can see that here, then this 5 can't produce two different y values. It can't produce the -1 and the 3. So it's not a function. Again, it's not part of the problem. This is still the inverse, but it's just not a function independently, that's all. Okay, not bad. Just thought I'd throw that out there before doing the last one of the day. So example 5, let's move to a different family of functions. Let's do quadratics. So box that up. And I guess we would sort of think of this as a nice looking parabola. And letter A, is the function one-to-one? If I asked you to graph this on the coordinate plane, would it pass the horizontal line test? No, the parabolas don't. So as a result, it's not one-to-one. So when we find the inverse, which we will momentarily, the inverse won't be a function by itself. But let's see if we can do it. So I'm going to do this right here. I'm just going to sort of create my rules. So let's talk about wrapping the gift and unwrapping the gift one more time today. So if I gave you an input, what would you do to get the output? You would square it. So square the input, and then you would probably subtract 1. Okay, so how would you go ahead and create the inverse of that function as a result? How would you unwrap the gift? Remember, start with the bow and work backwards. So I would go ahead probably and add 1 first. That would undo this step, of course. And then after adding the 1, I would undo the square. We'll talk about that piece on how we undo a square momentarily. All right. Well, here's how we're going to do it, at least for today. Start with your input, everybody. Start with x. And let's go ahead and perform the steps unwrapping the gift. Add 1. Okay. Once I add 1, now I'm with this right here, and I want to go ahead and undo the square. I undo a square with the square root. But notice my phrasing here. I was very careful to say that I'm undoing a square rather than just writing square root down. And the reason is, of course, and this should sort of, a little light should go on, anytime we talk about undoing a square, what do I have to remember, everyone? The plus and the minus. And that's the key. When you undo the square, those two parts of the root come out. And so as a matter of fact, that's your inverse right there. Okay. Good. So that's it. Add 1 and square root, but make sure you include both roots, the plus and minus. Well, let's see this all in action. Good culminating piece right here. So let's get rid of this stuff. And let's just type in x squared minus 1. I'm just going to hit graph for a second there. Notice it does not pass the horizontal line test. So when we go ahead and type in the inverse here, it won't be a function. And by the way, how will we know that it's not going to be a function, even just trying to type it in? Well, in order to get this in the calculator, I have to do it in 2 separate y equals. Do you see that? And the fact that I have to put it into 2 separate y equals, one for the positive root and one for the negative root, right automatically implies that it's not a function. And so we'll see this momentarily. I'm going to go ahead and get that going and then add one more thing. So there it is. And you can see, does that pass the vertical line test, everyone? No. And so it's not a function independently. Would love to see maybe the reflection line in place. Let's take a look at that piece. Yeah, not bad. You can tell a little more here than you could on the last one. Fold this part over, and it lands on this part. All right, perfect. Let's go domains and ranges on this. And here's what I'm thinking. First and foremost, the domain of every quadratic is all real numbers. So I'm going to go ahead and write that piece. So I can do any number in for the input, square it, and subtract 1. Not a problem. Which means, actually, without even thinking here, you could tell me one of the other three. And so right away, if the domain of the function is all reals, then the range of the inverse is also all reals. Okay, good. Now let's do this. We haven't done this before, but let's go domain on the inverse here. And what do we know about a square root? Well, in terms of that piece, we know that anything underneath that square root has to be greater than or equal to 0, which means, of course, x has to be greater than or equal to -1. And so our square root functions always have had conditions to it. And in this case, it looks like our domain is that. Which, and as mentioned before, we've been unable to pull this off. Don't forget, we are talking range, so please go y. And I know for a fact, even without having graphed it, or the need to graph it, I know that the range would be anything bigger than or equal to -1. Hey, let's bring that calculator up one more time and see it. What do you think? Domain, all reals, kind of going left to right, both directions. Range, same thing, all reals, down and up infinitely. Range of the function, take a look, from vertically, just from -1 up above. Domain of the inverse, take a look, from -1 to the right. And so it looks like it matches up perfectly. Last thing I'll do, and then wrap this on up, let's just track a point. Why not? How about x is 4? No, let's see, let's go 3. So there we go, 3, 8. And if I tracked that point, it would be 8, 3. There it is. All right, I'm hoping all those conclusions pretty much work out nicely for you. They all come together beautifully. If you have any questions, let me know. But as I said, we'll formalize this up a little bit on the next notes worksheet, Inverse Functions Day 2, where we'll take a look at some maybe different families of functions and see if we can find their inverses. Okay, anyway, in the meantime, get a little practice on this. Let me know if you have any questions, of course. And thank you for listening.